hear anyone yet.
Can you say something? Now I unmute you, so you could be heard.
Yeah, can you hear us?
Change the YouTube studio and change the title of the...
Can you hear us? So maybe not yet. Do I need to unmute? I know I'm through.
You should be heard
because you have the microphone you're into.
Okay, let's see.
Fair enough. But I can't hear anything. Let's see. I get a message now. So we'll see. I don't know. It should be fine. I'll just leave it like that, maybe. So he was here 5 minutes ago.
I mean, he's here. His screen is sharing.
Yeah.
Oh, is it?
Yeah. It's just like we can't hear him.
Oh, but shouldn't I see that too? Shouldn't I see that too?
Go to the refresh, and also you have to ask Kumavis to to give him all the rights.
I did. He should have it.
Okay, currently he's maybe rejoining because currently it's just you and me.
Oh, okay.
Or no?
Fair enough. No.
Screen is not shared.
So he's not.
His screen is not shared, but he is in.
Yeah, fair.
And you are unmuted, so you should be heard.
I should be heard, yeah. Yeah, it should be fine. Yeah, now we just have to wait and hope that it will work somehow. We're not live yet, no?
We are.
Oh, we are. Oh, great. Did we go live too early?
Sorry, the laptop looks really funny. With the microphones on, like ears.
Yeah. They're recording everything.
But Alex, why is it there? You could hold it.
Can you hear us? Oh, yeah, you can hear us. Oh, that's great.
Hello.
We can't hear you yet, though.
We can.
Oh, wait, can we?
Hey, this is Kumavis.
Can you say something again?
Can you make it super loud, Alex?
Yes, this is Kumavis. I'm coming to you
Oh,
from the
yeah,
other
yeah,
side
wait,
of the
wait, wait, wait.
world.
Oh, he's up there.
We can hear you, but you're quite silent. Let me. Maybe I have to make it louder.
Or just bring the mic.
Bring it down.
Okay, we have a Bluetooth speaker on top.
Is that your speaker?
Mic check,
Ours,
mic
yeah.
check.
OBS to see
Mic
if
check,
he's-
mic check. Mic check, mic check.
This sound.
Can you hear me?
Yes. What?
All good?
I think it's all good. Just Alex has to come back now because he went to pick up the speaker.
Cool.
Speakers come
I
to
can
us,
I
so
can
you
hear myself echoing, so
Yes.
let me just do a check.
Oh,
No, that's
I
us.
will mute. It's us. Can you say
Okay,
something?
great.
I will mute myself.
Hey, this is Kumavis coming to you live from the other side of the planet.
What?
Okay,
that
excellent.
Sounded cool, and you didn't hear yourself, right?
Yeah, fantastic.
Can you just share the
Okay.
screen so that I can also stream your screen, please? Yay!
Yeah.
Just a second.
Here
Okay,
we
now
go.
muting ourselves, and we are live with Lava Moat.
Cool. Hey everyone, this is Kumavis. Today I'll be talking about Lava Moat and JavaScript supply chain security. The title of this talk is The Attacker is Inside. Okay, so software supply chain security, what is that? Well, what's the software supply chain? That's everything and anything that touches an application, such as its dependencies, or plays a role in its development, like your bundler, your build tools, your CI system, everything. Sonatype has this cool timeline of supply chain attacks. And if you look through here, there's some Python, there's a little bit of Ruby, but it's at least 50% NPM on JavaScript supply chain attacks. So why is JavaScript targeted so often? One, and the primary reason, is it's so popular. It's used all over the place, front to back. There's a couple more nuanced reasons. One is ambient authority, and I'll show what that looks like. But then it just means if you get to run JavaScript, you get all the powers that are in that JavaScript environment simply by being able to run code. And the other thing is, in JavaScript, by default, everything is mutable. Well, we can see how we can use that to our advantage as an attacker. Okay, so it's popular, right? This is the Stack Overflow developer survey, and JavaScript is at the top of the pack there. We're looking at all respondents. If you sort by professional developers, it doesn't change very much. There's a bit more TypeScript usage, but yeah, JavaScript is just really strong. The NPM registry is at just shy of 2.5 million packages and something like tens of billions of downloads per month. It's just a very vibrant ecosystem. So that's the main reason it's popular. That makes it a juicy target. But there's a couple other things, and let's put our mischievous thinking caps on to see what we can do as an attacker. So let's say we have control of this package. It's used for normalizing Unicode, and it's used by a application that we want to attack. Well, because of ambient authority, simply because we're some module in the code base, we have a lot of powers available to us. So let's say we get access to the network, we have access to environment variables, if this is like on Node or something. And we could just send the environment variables to our evil website, and it might have things like API keys and stuff like this. Well, honestly, that was too easy, and so it was pretty boring. But yeah, this is, all your modules have access to stuff like this just because you import them. Now let's look at mutable. This one's a little more subtle. Okay, so in this example, I have some secrets. I created an array of 3 secrets. We have this function check secret that you can make a guess and see if it's one of those secrets. And then I'm going to wrap it in a block so you can't get reference to the secrets. That's my intention. I'll just kind of export the check secret function. And so then I can make a guess on the outside and try to see if I can figure out one of these in here. And you might have said like, oh, well, you could just brute force it then. Okay, so I'll add a restriction. You can only get 3 guesses, right? So how are you going to get the secrets in there? It's all locked away in the block. I'll leave a moment for some guesses. It's a weird one. Okay, so you can overwrite array.prototype includes, which gets a reference to the secrets when check secret is called. So inside of here, when it's doing secrets.includes, it's walking the prototype chain of secrets, going to array.prototype.includes, and calling it with this value set to the secrets in there. So even though we were outside this block, and we only had access to check secrets, we were able to steal the secrets. Because everything is mutable in JavaScript, even the built-in primitives. Okay, so we have our tricks up our sleeves. Let's talk about JavaScript supply chain security now. So JavaScript supply chain security, we're talking about like your app's dependencies, your NPM deps, but not just the NPM deps that you add to your package JSON. Those deps have deps, and those deps have deps. So you have this large dependency graph, and not just the ones that you use directly in your application. There's your build system and all your other tools like your linter and stuff, and they all have dependencies. And so all of this is part of the JavaScript supply chain security. And so to understand what a supply chain security attack looks like, let's look at the Copay wallet hack. This was what really got me interested in trying to solve this problem. It's an interesting study in general. It's a very targeted attack. At the time, you may have heard of it, known as the event stream incident. It made a lot of news. This is about 2018, the end of 2018. And so we're kind of like this. Here's your normal build phase for building an application, right? You got your dependencies that you install, and then you run a build process, creates an app and you distribute it to your users. Could be a web app, could be a web extension, what have you, a mobile app. And in this case, we're talking about a self-custodied cryptocurrency wallet. So the private keys are in the application only. They're not on the server or anywhere else. They're only in that user's application because the user created them. It is a cryptocurrency wallet, but it could have been, a web app with a credit card form or just a password field. Users deal with secrets on their machines, even if they never leave those machines. And so this is where the attack happened, here at runtime in the distributed software. But the evil dependency was actually not part of the application dependency, it was part of the dev dependencies. When it was initialized, it went onto disk and modified another module that was part of the front-end dependency graph. But the attack also could have happened here. So when you need to secure these things, you got to secure the whole pipeline. In the case of deps install, there's all these lifecycle scripts. There's post install and things like this, and you just get to run a command on the machine when the package finishes installing. And the attack that could easily include an attack payload. So Jackson Palmer from Dogecoin summed this up saying, BitPay, the author of the CoPay wallet, essentially trusted all the upstream developers, you're just talking about the dependency developers, trusted all the upstream developers to never inject malicious code into their wallet. And that sounds pretty bad. And it is pretty bad, but it's also just the standard way that we make JavaScript applications and build on open source. So yeah, how can we fix this? What can we do about this? There's a lot of discussion at the time, and a lot of long conversations. Some people said, should we never use dependencies? What? Are we giving up on open source and collaboration? That doesn't sound like a great solution. Audit all dependencies always? I mean, yeah, fantastic idea, but that might be really impractical. How many dependencies do you have? Hundreds? Thousands? Tens of thousands? And when you need to push a security fix in your application and it involves updating dependencies, can you stop and put that security fix on hold and audit all the dependencies? You may or may not be able to do that. So is there a third way? Is there something else we could do? About this time, I got introduced to Agoric and their Endo.js, their hardened JavaScript toolkit. Okay, so the toolkit provides two things. There's a core part of Endo.js called SES, and it provides this lockdown function. That calls object.freeze on the object prototype, on the array prototype, and prevents the modifications to those basic JavaScript functionality, kind of like in the example that we saw before, where the array prototype includes was overwritten. This gives us protection against those kinds of modification attacks. Okay, the other part it gives us is compartments. This is where we can deal with ambient authority. So you create this compartment, you give it the endowments, the things that it should only need access to, and then you can evaluate some code in that compartment. So let's say we only want to give it fetch for network access, and we only want to give it location, the current URL of the website we're on, or it needs to know the path or something like this. So you could set it up like that, and then run your module inside of there. This is really useful, but I didn't think it was possible without a modified JavaScript runtime. But it turns out you can do it with a shim in just any JavaScript environment. And it works in two ways. It uses two weird parts of JavaScript that you may have never heard of before. One is called the with statement. The with statement has a with keyword. It takes a target, and then it has a block. And the way this works is any properties on the target are considered like variables in scope inside the block. So here we can just reference ABC, which happens to be on the object. This is not particularly useful on its own. It's actually also kind of deprecated in that it's not allowed outside. It's not allowed in strict mode, And if you're using ESM, you're automatically in strict mode. But yeah, this is just a weird corner of the JavaScript language. And on its own, not particularly useful. And then there's the proxy. The proxy, if you're familiar with like getters and setters, the proxy has that programmatic interface for any action taken on an object. So for any property, you don't need to know the property ahead of time. And so there's that. And then combining those two, we can do this. We have the with keyword, we got the proxy in here, and then you put the untrusted code in here. And then whenever that tries to reference something that's not, like immediately in scope in here, it'll go up to this proxy and it asks the proxy, do you have this thing? And it gives the proxy an opportunity to say, yes, you can have it, it's this value, or no, you can't have it. And it can like throw a reference error or something like that. So then it turns out when you have just one proxy doing all the things in there, it ends up being a bit complicated in implementation. If you split it into a couple of pieces, what you can do is this internal piece is just that object, just that object full of things we wanted to make available, be it fetch or location. So that's just a normal object in there that we want to be in scope. And then up here, we just have the scope terminator, which always says, no, you can't have access to the thing. So with this setup, you're pretty much done. There's a couple other things you need. Let's see. On the inside, you need to make sure that untrusted code's actually running in strict mode, primarily to make sure you're not you're reducing access to the global this, the unprotected global this. And then one more thing, you got to tame the function constructor, which works kind of like an eval statement. So this is actually done as part of the lockdown. So you do that, and now you've got a safe little container there. And then if you want to use, you want to turn it into an evaluator that you could reuse in different situations, you can add eval in there. Then you need to add this other layer that just lets eval get accessed once before the code actually is run. But it's pretty easy in implementation. Okay, now that is pretty much perfect shim. But that's that's a bit complicated. You don't need to use that. You can just use this simple API. Pass in the things you want to have access to, pass the code you want to run. And then just a couple notes about it. Let's see, if you're familiar with the Node.js's VM built-in module, you get something very similar, right? You can do VM, run in context, you got the code, and then you have the things you want to be exposed to that code. And you can build a similar construction with iframes in the browser. If you set up an iframe in the same origin, you can actually interact with it, not with post message. You can just do like iframe.contentWindow.eval and then have direct access to objects and pass across. But this is different than a compartment. This is a different realm, as we call it. And when you're dealing across realm boundaries, you have this problem called the identity discontinuity, where my capital A array is not your capital A array, and that breaks things like instance of array. So while this is a useful tool, having access to these realm boundaries, or having access to different realms, it's really not great for backwards compatibility. If you have this graph of modules or this application, and your modules are expected to run in the same realm, when they're suddenly running in different realms, it can get confused. So nice thing about compartments, while they do have different global objects for each compartment, they have the same intrinsics, the same basic JavaScript features, and so things don't get confused. Okay, so that's pretty neat. Let's go up a step higher and look at Lava Moat. So Lava Moat is first and foremost a set of security tools for any JavaScript application to help mitigate software supply chain risks. And in particular, one of the key features of it is the Lava Moat kernel, which wraps each package in its own compartment and only gives it access to what you've deemed it necessary for each package. So it looks like this. When you run your application or you create your application bundle with Lava Moat, you have your Lava Moat kernel here at the bottom. it comes with the policy, and for each package, including your app code, including this dependency, that dependency, it creates a package for each of those, or a compartment for each of those, and they only get access to what they need. And then, say in the case of ComJS, it's threading in a require statement, so these things can access each other and import each other. When you use it, where previously you might have run node index, you can run lava mode index and generate a policy, and then next time you run it, it will use that policy. So you just basically switch out node for lava mode. And so the policy looks something like this. This is for one package, but your policy will include all the packages in your dependency graph. We have the built-in, these are built-in packages, and we separate them from like npm user space packages because, say, they might pass on capabilities like access to the file system. Then there's also globals, like here's access to the current working directory. That's not too dangerous, but there it is. And then these are the other packages that you're allowed to access. So you get a little readout for each package, and it's your responsibility to review these, and then when you run with LavaMoat will enforce them. And then because the policies can be quite big, we have this little visualization dashboard for them. This is a dependency graph for the front end. This is WebTorrent. Here, the purple node is your application code, and all the others are packages. And then they're colored by a very, very rough heuristic of dangerousness. All the green ones only import other modules. They don't access any globals and don't import any built-ins. Well, we don't have built-ins in the browser, but so then the red ones are just using potentially dangerous global APIs. But it gives you an opportunity to sort of prioritize your audit or dig around and look for things that might be dangerous. Most of them are colored dangerous, even though they're accessing very undangerous things. Let's see if we can find something that might. Yeah, these ones are just timeouts. That's not too interesting. Yeah, if this visualization doesn't know about your API, it won't be marked as like safe or maybe safe. So it just defaults to dangerous. So I'm having trouble finding something that's obviously dangerous, but this gives you a little overview of what you're dealing with. And then if you, the thing about LavaMoat is so here we've identified some potentially dangerous ones you might want to prioritize in your review, but without LavaMoat, you don't get that, right? Like any of these packages could invoke any global API, and so it's hard to even know where to get started in looking for vulnerabilities in your application. Okay, so back to the build pipeline. We have tools for each step here. For the deps install, if you add LavaMoat allow scripts to your application, it will turn off all scripts, lifecycle scripts, post-install, whatnot, by default, and then you can opt into the ones that you need to run. If you need to run any, say, I don't know, Electron might need a build for your system. And then at the build step, you just run your bundler in LavaMoat node, if it's a node application, and then to produce the runtime and get the runtime in your application, you want to add a plugin for your bundler. So we have one for Browserify, we're working on one for Webpack, we're working on one for React Native. And we need your help. LavaMoat is open source, and Endo.js is open source. You can find them both on GitHub. We're trying to make this space safe for everyone, both for the people consuming packages that want to do so safely, and for people to produce packages, so they don't have to worry about who ends up using your package and if it's secure. So that was an overview of LavaMoat. Thanks for listening. Now we have some time for Q&A if you like.
Yeah, thank you very much. Can you hear me?
Yeah.
Okay, perfect. Yeah, that was very interesting. I'm wondering, do you maybe by any chance have plans or already use it in Metamask?
Yeah. So this is deployed in the Metamask extension to 20 million users. So this does work in production. We have a very large dependency graph, and there's only a few cases where there were some compatibility issues, and we use this utility called patch package to go in and make the small changes that are necessary. And then if we get a chance, we also make that change back on, pull requests back upstream.
That sounds cool. How big? Like, if I want to use it in my web app or web page, how much in terms of size does that add to my bundle?
Yeah, that's a great question. I don't have a number off the top of my head. The it's not too big. We're not doing there's no need to do like transformation of code in the application or anything like that. We just put those little with statements around your thing, and then there's the kernel itself is not very big. There is a bit of a performance impact by putting you inside of the with blocks. We're taking you off of the hot path on V8 sometimes. So I've seen slowdowns at like 2.1x for compute. In general, you're just waiting for user interaction or network or something like that, and so you're not really pegged on compute. If you're doing we do have one really bad case, which is if you're doing something like heavy like cryptography using typed arrays, they get really slow. But in general, performance has been fine. And we have our 3D Fox head, and that renders fine inside of Lava Mode. Like there's no performance issue there. So in general, you can add it and not notice a difference.
That sounds cool. I'm wondering, like, regarding the policies. I mean, you showed some. Can you maybe, for example, for the cryptography dependency, can you just deactivate Lava Mode for a specific module, which you actually maybe audit to avoid the slowdown?
Yeah, we have an option for that in Lava Mode node. For example, we're using the SAS compiler. The SAS compiles SAS code down to CSS, and it's written in Dart, and Dart can compile to JavaScript. But Dart compiled JavaScript is really sensitive to its realm, and we had it did not want to run in a lockdown realm. So I added an option that can fit in the policy where it actually runs it in an unfrozen environment, and that worked great.
So does that mean I can, for a certain dependency, just say run it in an unfrozen environment, and therefore it becomes fast again?
Yeah, exactly. So we just ran that one outside the safety barrier, and it worked great. You do need so like we were talking about this performance issue with typed arrays. You do need to put it in another realm. So if you're in the browser, we need a means of like opening an iframe and running it over there. Or if you're on Node, we can use the VM to create this separate realm. And then just that one package gets run over there, and it can still have dependencies that run over in the main realm and are locked down safely. So you can do it on a per package basis.
That's cool. I'm wondering. You said you don't know exactly how large how much code it adds, but like you showed those little with statements with the proxy. I mean, that looks like literally like a few lines of code. There's like nothing. So I assume it's like more kilobytes, not a megabyte or something. When you add that.
Yeah, that's right. Yeah. It's really not a ton of code.
That's cool. Also, I think you showed that you were using eval, but you had like this extra proxy that maybe counts or whatever, and after one-time use of eval, it doesn't use it anymore. So if everything is like the primordials or the runtime environment is frozen, what could be wrong with using eval more than once? Is there like a specific issue with that?
Oh yeah, so um, this is, so you can still, say, run code that accesses eval, and you can give it a safe eval. But what this is, and what I mean safe is like defined to, it's confined to that same container, the compartment that you defined. And so when we're doing this, like in the browser, we don't use eval, we don't have this layer. We do it like this, and we just template in your code here. So we just take your module and we drop it in here, and that becomes your module definition. But in order to give this API, where there's basically this eval function here, then we need this construction with the eval and the get eval once. And the reason for giving it only once is this eval could be used unsafely to escape the compartment, and so we use it here, but we can't give access to it in there. So we need to make sure it's used once, and it's used once by this thing, which is part of the construction. And then by the time your code runs, it's not available anymore. But we can still expose like a safe one. So if something calls eval in here, it'll wind up in the same exact place. So it's used once per evaluator, and then you might create multiple evaluators.
All right, that sounds great. There's another question from the audience.
Yeah.
Hi, I'm just a little bit curious, like for like other bundlers and stuff. How does it play with like rollup or ES build, or like if you already have some kind of setup for it?
Yeah. So roll-up's probably more possible. I looked at ES build, and the way their plugin system work, it did not seem particularly extensible. And so that was one reason why we went with Browserify, is that it's just so easy to hack on, and I've worked with it for a long time, so it was really familiar. So that's what we were using in MetaMask already. Our next priority target is Webpack, just because it's used the most common, but it's not part of our toolchain right now, so we don't have a lot of pressure to get it working for our own needs. React Native is a tricky one. Yeah, actually, we're maybe React Native is a higher priority for us than Webpack, just because we are using it for our mobile client, and it's also similarly kind of inflexible. So we're being very clever in how we make our integration. It involves like running a patch to some React Native build tools. And if we find something that works the way we want it, then we'll try to get it working upstream as well. But yeah, it really depends on how flexible the build system is.
Okay, nice. Well, good to hear.
Great. I was wondering, like, do you know how many users, or in how many places is Lava Mode used already? Is there maybe, for example, in the browser, I could imagine, like usually you have like the the origin to make sure that like different apps cannot, without maybe some opt-in by using iframes and post message or some other workarounds, communicate. But I imagine maybe you could even have multiple apps running in the same web page, and they're kind of shielded from each other because they're using all Lava Mode. What are people using it for? If you know, like, what would be some examples? Is something like that possible?
Yeah, great question. So I know Lava Mode allow scripts has been picked up and used in a few different places. Now, this one is definitely the easiest one to integrate. You can start this right now. And Lava Mode allow scripts. It comes with this companion piece called post-install always fail. So it's got this dependency that just throws an error if its lifecycle script gets run, and it's a nice safety to make sure that you have it all set up correctly. But yeah, this doesn't care about what bundler you're using or anything, so this is nice to good place to start. It stops all those dependencies from just being able to shell out random stuff into your computer. The next layer, Lava Moat. No, this is pretty general. I don't know how many people are using it right now. And then, yeah, I mean, not a lot of people use Browserify these days. So I think the actual numbers for runtime protection are pretty low. I mean, we're happy that we're able to ship it to 20 million people, but we really got to make this available to more developers. And so I think Webpack is a good key to that. We've also been looking at sort of jumping ahead to the next generation of tools. There's some effort to get SWIC, SWC, the bundler built in Rust, working and spitting out packages defined inside of compartments. But yeah, the most uptick I've seen right now is in Love allow scripts.
Cool. So the way I would use it, instead of running my script with Node, I would maybe run it with Lava Mode Node. And then if I want to
Yeah,
build
that's-
a browser, I would just add the Lava Mode X plugin into my build chain.
Yeah. So right now we just really have the Lava Moat Browserify plugin, but the Lava Moat Webpack plugin we'll hopefully have ready soon. And if you like writing Webpack plugins, please come help. And yeah, similarly, if it's possible to build a plugin for your bundler, we can take a look at that.
I mean, we're happy because we're anyway using Browserify, so there's no problem for us at least.
Nice, fantastic.
Cool, yeah. Thank you. That was an amazing talk, very inspiring, and I'll definitely will try it out soon.
Cool, yeah. And if people are feeling mischievous and want to see if they can like break the sandbox, please take a whack at it. And happy to explain why it's safe against these things. We spent I got together with the Agoric folks. We spent like a week trying to break it, and we got some partial breakages, but we never made it all the way through. So we're pretty happy with its security. It has like a 10-year history. It started inside of Google as part of the Kaha project, and then was broken out as a smaller, simpler piece. They found that they were trying to do whole sandboxing of the DOM and stuff like this, and they just found that the DOM was basically an intractable problem, and then broke off SAS, the container and the compartment and lockdown piece.
That's so cool. So you're using SAS or maybe Endo as a dependency for Lava Mode?
Yeah, it provides the compartment and lockdown parts, and we build on top of it. They also, so in the time that I built Lava Moat, which is that sort of abstraction layer on top of the compartment, they built a similar thing. They're working on making Endo into an alternate node runtime. And so you have your node, you have Dino, and you have Endo, and Endo's built object capability security first. And Lava Moat was more like, this is fantastic, let's get stuff that people already have working and safe. And so Endo's a bit more like forward-facing, Lava Moat's a bit more backwards-compatible facing, and we're trying to like merge the efforts into one thing.
But Lava Mode Node is not a runtime? I mean, it looks like one.
You use it like a runtime, but it just runs node, starts its kernel, and then enters on your entry point inside the Lava Moat kernel. So when you like we were looking at the policy, all these things, you're getting the Node.js built-in packages here. So if your thing's built to run in Node.js, it'll work in Lava Moat Node.
Does it use like loaders or something?
We didn't go with loaders. It basically just is sort of it has the functionality of Node.js rebuilt into it, and then pokes holes back into the Node.js system, like with built-ins and globals. So like when you write a module and it's getting executed in Lava Moat Node and it's expecting, say if it's CommonJS, it's expecting a require function and stuff. That require function is coming from Lava Moat, and it's specially, it's implemented by Lava Moat.
All right.
But But then when you want like the file system, you're getting the real file system object from Node.js, and we're just passing it through.
Then one more question. I guess that's the policy file or an example of it, and it says browser pack, which I assume applies to the entire bundle. But you could.
Oh, this is Sorry, this is just one. This is the name of a package that appears inside the policy, and you would have one of these for each of your packages inside that one policy.
So you have like one large object, and the properties would be all the module names, maybe with versions, and then you have those permissions for each of them.
Yeah, that's basically what we have. And then it's all automatically generated, like it's using static analysis to see what the package appears to be using, puts that in the policy, and then you can modify the policy if you want.
So if it's supposed to shield against some malicious, are there maybe edge cases where it's hard to find it with static analysis, and it would kind of just sneak in something that goes undetected, or?
Oh yeah, this is my favorite part. So like static analysis is great, but when you use it as a security barrier, it's very limited because if you miss something, and it's easy to miss something in static analysis. So if that's your safety layer or your security layer, you're gonna have a bad time. But what we're using it for here is just for convenience. We use the static analysis to generate the policy. And then if we miss something, you go and modify the policy and make some changes. But in Metamask, we have tens of thousands of dependencies, and we only make a small handful of changes. It really works quite well.
Interesting. I was just wondering, maybe we will even have Ferris talking about socket dev, but I mean, they're also doing lots of security analysis for the NPM ecosystem and supply chains. Can that be useful? I'm not sure if it's available through an API or something, but
Socket Dev is fantastic, and we're using it in MetaMask as well. So it's like they may have some other things, but they have a GitHub action, and so when someone makes a pull request and it changes dependencies, it'll go look at the new dependencies, see if they added new lifecycle scripts, which might be a red flag. We'll see if they're adding native code, that could be a red flag. And so you get a little report in your GitHub pull request, and it's really nice. I think, but it's totally orthogonal to what LavaMoat is doing. Like, they don't have a ton of overlap, other than they're both in the category of supply chain security. Those reports from Socket Dev are fantastic. They are letting you know about potentially dangerous changes before you merge your pull request. And then what LavaMoat's doing is it's protecting you at runtime. And LavaMoat and like Endo are the only tools that I've seen that actually provide runtime protections against supply chain. So that's where we're unique.
Can whatever Socket Dev analyzes, can that help in informing the policy, like to make it more refined than just a static analysis?
I don't know if Socket Dev is going beyond static analysis at this point. I'd love to look at their tooling. They may have more sophisticated static analysis than we do. But actually, if you look at this isn't the best example, but here you can see it's not FS. It's fs.readFileSync, and when we provide when we make the compartment for here for this package, we have this kind of container for the value of fs, and it has the actual read file sync from the Node.js system, but only that. And so we're looking. We see that they're only using one part in here, and they could like be importing fs, like const fs equals require fs, and then only use fs.readFileSync lower, and we recognize that. We trace the reference through the code and see that they're only using one. And we can follow it through destructuring and reassignment and variables, and we see just what you're using. And the fidelity has been great. So been pretty happy with our static analysis.
All right. Yeah. Thank you very much for this inspiring talk and for walking us through how it works. We'll definitely give it a try.
Yeah, you bet. So yeah, my name's Kumavis, Kumavis. You can find me on Twitter and GitHub. Feel free to say hi. Don't be a stranger.
Sweet. And the project is Lava Moat, and the other one was Endo, right?
Yeah, ENDO. You got Node, Dino, and Endo.
Oh, I see. Oh, okay. Yeah, that makes sense. I didn't think of that. Cool.
Okay.
All right.
Thanks. Thanks for having me.
Yeah. Thank you for sharing with us. See you.